One question that keeps coming up is problem on the project where we look at implementing a digital filter. The way I set up the problem is similar to what I have right here. All right, so in this particular case, what I have is an inductor and a resistor instead of a resistor and a capacitor. And what I say is, imagine that my voltage source here, which I'm going to call x of t, that's my input. So this would be the distorted audio file that you have. Okay, that audio file that I gave you is a sampled version of some real voltage. In other words, I can take an audio signal. An audio signal is a voltage that would have to be sent to a speaker or something like that to listen to it. I can sample that voltage. Okay, so in this particular case, in this problem, right, I have my x. All right, so my x is just a series of numbers. All right, and I should be careful as always to check to see how big is it. So size x is pretty large. Okay, so 73,113 rows by one column. Always check that, right? That size command to figure out what the dimensions are, because that may be important as I go through this. Okay, all right. Now, in this case, y of t is my output. All right, this circuit is a filter, and what I'm trying to do is I am trying to construct a filter, a digital filter, by creating a digital analog of this real circuit. Okay, so in this particular case, because I have my, I guess what I really have is I have an x of n. All right, when I say x of n, what I say is that I have in this vector a series of numbers, x of 1, x of 2, so on and so forth, all the way up to whatever the last value is. So in this case, I don't know, whatever that is, 73,113. Okay, I have all of those entries written in one big column. To create x of t, all right, x of t, if x of t is a time vector that would go out to my audio card or my sound card, right? In Matlab, there's no such meaning as time. All right, so what I end up doing is when I call the sound command, I say x comma fs. Basically, what's the rate at which I want to shoot these values over to the sound card? All right, so in that case, what x of t would do, x of t would be, the way I look at this, x of t, if I could imagine that vector in Matlab, it would be x of 0. Then, so this would be the first entry. All right. Then the next one would be delta t. The next one would be at 2 delta t, etc. Right. So x2 would be at delta t. x3 would be here, so on and so forth. Right. That's the way this guy sort of functions. All right. So in this particular case, my delta t that I'm going to choose is based on my audio. So my delta t that I'm going to choose is 1 over the sampling frequency. Okay. Now the question is, how do I create the filter? Well, to create the filter, I start with the circuit and say, well, imagine what I was doing is playing this audio. So playing this vector of numbers at a rate delta t. Okay, so this guy here would be what I would effectively say, I want to be sending this voltage through this filter. Okay, so I want to figure out how I would create that filtering. So to do that, I have to create a differential equation. So I'm trying to find the voltage y of t. Okay, y of t is equal to the voltage across that inductor, right? So how do I figure that out? Well, there's a couple of ways here. So I know that VL equals L dIL by dt. So I have to be able to figure out, well, what is IL in this particular case? Well, in looking at this, the way that I see it is IL is the current through this circuit. IL is equal to the voltage across the resistor. So the voltage across the resistor divided by the resistor is that current. So if I called that voltage VR, and then VR divided by R is that's the current through there. And I can define the voltage across the resistor in terms of the two node voltages. So the node voltage on one side of the resistor, the plus side, right? In other words, what I'm saying is that VR is equal to X minus Y. The voltage at the plus terminal minus the voltage at the negative terminal. Okay? So I say X minus Y over R. And then I plug that back into here. Okay? So what I get is that Y of t equals L over R times d by dt of X minus Y. Because the derivative operator is linear, I say that I have dx by dt minus dy by dt, like so. Okay? Now, what I do at this point, let's write it down here. Y of t equals, I'm not going to write L over R because I know I'm going to make mistakes when I do that. So I'm going to say tau equals L over R. Alright, so I have fewer things to hang around. And then I bring in here basically my definitions of the derivative, right? So again, we said that I get a dx by dt is approximately the same as this, and that dy by dt is approximately the same as this. Okay? And I plug those into, I basically drop the approximation, say I make delta t small enough, plug it into there, and I'm good to go. Alright, so I say that y of t equals tau times dx by dt minus tau times dy by dt, or that I get tau times x of t plus delta t minus x of t all over delta t minus tau times y of t plus delta t minus y of t all over delta t. Okay, so now what do I want to do? Well, I want to solve for y of t plus delta t. So I can do that all right, by essentially bringing, let's get the y of t plus delta t all by itself. Okay, so I'm going to say I have minus tau over delta t times y of t plus delta t. Okay, that has to be equal to y of t, and then I'd have to bring this term over to the other side. So I say minus tau over delta t times x of t plus delta t minus x of t. And then I have to bring over this term over here with the y of t. So that's going to become minus y of t times tau over delta t, like so. Okay, so what do I do now? So basically I have to multiply both sides by minus tau over delta t. So I do that. And I am going to end up with y of t minus tau over delta t times y of t plus x of t plus delta t minus x of t, like that. Okay, so that is what I get in the end. Now this is what I want to bring into MATLAB. Now the thing is, if we've taken time and discretized it up, remember that x of t has been sampled, which means that it's been dumped into a row of numbers, x1, x2, so on and so forth, down to x of n, however many points I have, okay? So the value that I get at x of t plus delta t, the way I can think of this as the value at time t is the nth value in my vector, and the value at t plus delta t would be the value at n plus 1 time step ahead. Okay, so the way I would put this into MATLAB is I say y of n plus 1 equals y of n minus tau over delta t times y of n, times y of n plus x of n plus 1 minus x of n. Okay, that's how I code that guy in. So this is the thing I want to code. Okay, so I want to code that in, and let's go to my Matlab code. All right, so here's how I did it. I took the same file that I told you guys to use, and then I said x equals 3 times y, okay, delta t equals 1 over fs, and then what I do is I initialize the vector. All right, so I initialize my output. My output is going to be, for right now, I say it's just equal to 1 entry, and that's the number 0. Now, how did I come up with that? I said, well, what's the initial response that I expect to get from this circuit? All right, I don't technically know what the first value is when I jump in here. I need some initial condition. Now, if I'm playing out the audio at the end of this, I'm not going to hear one data point. I'm updating points at a rate of 8,192 hertz. Okay, that's pretty fast. And so I'm not going to hear one point. So I could probably pick any number I wanted here, but I'm going to say, let's assume that this output voltage here in this circuit started out at 0. That's a reasonable choice. Now, what I've done is I've set R equal to 1 and L equal to 318.31 microhenries. Okay, very similar to what you guys have in the assignment, but you have basically an RC circuit rather than an LR circuit. Okay, so I defined that tau equals L over R. I had defined that over here when I went through my math. All right, and then I set up a for loop. All right, that says I'm going to loop from n equal to 1 in steps of 1 to a particular stopping value, and then I brought in the equation that I had written over here. Okay, the thing I got to be careful of here is, I've said before, I want to manage my expectations. So what do I expect to get out of this? Well, what I expect to get out of this is some vector here, y, that should have as many entries as x does. Okay, and so we'll just think about this mentally. When n equals 1, I'm going to be computing y of 2 using y of 1. So that's why I need the initial condition. And using x of 2 and x of 1. All right? So if I keep going with this, I'm always generating the next value. So when n equals 2, I'm generating y3. When n equals 3, I'm generating y4. When n equals 4, I'm generating y5. The problem that you run into with this, I keep going. Let's say n equals 1 to 1 to length of x. Okay, so let's just check for ourselves. What is the length of x? So the length of x, 73,113. All right. So let's think about what's going to happen when I get to entry number 73,113. Okay, I'm going to say that y of 73,114 is equal to whatever the last value of y was, minus the last value of y times this delta t over tau, plus the value in the x at entry 73,114. That doesn't exist. Okay? So because it doesn't exist, I'm going to say go until length of x minus 1. Okay? Length of x minus 1 means that the last time I'm in this loop and I say x of this value plus 1, I'm going to be able to get the last entry in this matrix. Okay? So once that's done, I'll run this code. All right, so it ran. So let's listen to my original signal. And then let's listen to the filtered signal. Much better. All right. If you do the analysis on this, it's because I have a high-pass filter, and I've removed this sort of 60 hertz signal that's embedded inside there. And if I wanted to see that signal, one thing I could do for myself is, let me make a time vector. T equals 0 to 1, 2. So I'm going to make a vector that goes length of x minus 1 times my delta t. Now, why did I do this from 0 to 1 to length of x minus 1? All right. Well, if I looked at the size of this vector, and again, always thinking about sort of what I expect my results to be. So let me do this. Length of that vector, so 0 to 1 to 1, the length x1. Oops, I gotta put my parentheses on there. That guy is 73,113 points long. If I had said to length of x, it would have been 1 longer than my x, and my plot command requires me to have two vectors that are the same length. Okay? Now, I took this guy and I said multiply it by delta t. What this is going to do is this response right here is going to create a series of integers, okay, like that. So look at my entries: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so on and so forth. So if I multiply by delta t, I'm saying my entries are going to be 0, delta t, 2 delta t, 3 delta t, 4 delta t, so on and so forth. All right, so now let's just plot this guy. Figure 1, plot t, comma x. And let's run that. All right, now it's plotted. Now, one thing I wanted to show you real quick. Let's zoom in. So I got to hover over the graph, choose the plus sign here. I'm going to zoom in on a portion of this guy. All right. What you can see is there's this big waveform in here. That's the noise that I'm hearing. So I'm going to use my data tip. So I click on the data tip, put 1 here, and then I right-click on the graph to create new data tip. And I'm going to try to create a new data tip over there and move this one here. All right, so I'm basically near the peak of the waveform in both cases here, just about near the peak of the waveform. And I'm going to do what's the time between those values. The x coordinate's 2.267. Move this guy over here. So the x coordinate of one of those data tips is 2.267 seconds. Minus 2.25 seconds. I see that there's 17 milliseconds in between those two guys, or 1 over, it's about 58, 59 hertz, something like that. That's the signal that you're hearing, this in the background. that guy is largely removed once I run the filter. Okay. Now, one thing I want to talk about here real quick, let's say I hadn't done that length x minus 1 here, and I ran this guy. Index exceeds the number of array elements, 73,113. So let me do right now, I can always check to see what's happened to my code. If I type n, I see that n currently equals 73,113. That means that it's saying y of 73,113 minus y of 73,113 times this guy plus x of 73,114. Well, that doesn't exist, so that's where the error comes from. So you have to think about, in your mind, usually what's going to happen at the first entry and what's going to happen at the last value. So you usually have to think about what's going to happen at n equal to 1 and what's going to happen at n equal to the end value to make sure that I've got everything set up right. Usually the problems that you run into in for loops happen at the first time through the for loop or the last time through the for loop. All right, so you have to think carefully about what your code's going to do. All right, hopefully that helps a little bit on some problems like this one.